afternoon, everybody. Thank you for being here. I work as a principal machine learning scientist at Booking.com. And today I'm going to talk about the main principles of how we moved from our current experimentation platform, or let's say we're still moving, to an adaptive experimentation platform that is also subpopulation aware. I will explain during the talk what actually this means. So this work I'm presenting here was a collaborative work with a lot of institutes, including CWI. Let me start by saying that in Booking, before we deploy any new idea, any new algorithm, any new product, we first have to make sure that it is beneficial for the customers. So the way to do this is with online control trials or A/B testing. So we have a version A, which is the default product, that is the control, and the version B, which is the competitor of the control. We randomly split the traffic to either view version A or version B, and the version that gets highest conversion rate, higher clicks, or is better in any type of business metric, is deemed the winner and gets deployed. In reality, it doesn't have to be just one alternative version. We might have multiple alternative versions competing against the control. And in that case, we would call this an ABN testing. In Booking, we would use it in two ways. One way would be for decision making. So we want to find what is the best variant so that we can deploy it in production. But another way would be to actually learn from the experiment data. So we can take the experiment outcomes and then combine them with information such as how much does it cost to maintain the solution in production? Or does it fit a broader strategic plan? Or does user research agree? So in this case, we are not looking per se for the best variant to deploy, but we're looking for a subset of options, of promising options. And these will be the ones that are better than the control. So how do we solve this problem with the current non-adaptive experimentation platform? So again, I have a control. Let's assume I have a control and I have K different variants. I'm looking for the variants that are better than the control, just to be more clear. So we have a K number of independent null hypotheses. And then for a fixed risk delta, which would represent the probability, the false positive chance, the experimenters will have to determine a minimum desired effect size. That's the effect size they want to see. And with this effect size, they need to do a calculation of what's the sample size that they need to detect this effect size with a high probability. Then we will distribute the traffic uniformly across all the variants. And at the sample, when the nth participant enters the trial, we're going to compute the p-values and the ones that are per hypothesis, and the p-values that are lower than a certain threshold are going to reject the null hypothesis. So I'm going to consider these arms as the better than the control. Here, my threshold is delta divided by K because I want my overall error. I'm conducting K hypothesis. I want to keep this at this delta level. Now, this process is straightforward, but it has certain disadvantages. The first one being that I have the uniform allocation of users to the variance. Now, if I assume that I actually know the values, let's say the average conversion or the average click rate of each of these variants, since my goal is to distinguish between the control and any of the other variants, I would probably need to spend more effort in distinguishing the smaller differences. So in this case, that's the difference between control and variant one. If I do a uniform allocation, I will either miss the effect of variant one if my sample size is small, or if my sample size is large enough to detect the effect of variant one, I'm going to waste also that sample size for the other variants that I don't really need it for. So a better way would be to just send more samples to control and variant one, for example, where I want to discriminate better, and then throw fewer samples to variant two and even less to variant one, to variant K that is further away from the control. Another problem is that we do not allow experimenters to monitor continuously their experiment as they go. Of course, the experimenters would like to be able to stop the trial as soon as possible because there is an opportunity cost in longer trials. So they want to see the effect as soon as it comes, or they want to abandon the trial as soon as they see there is no effect coming. This makes a lot of sense, but as we said, we need to fix the sample size, and we're not allowed to do data-dependent stopping times. And here I have some sort of a visual explanation of why we're not doing this. Here I'm plotting the p-value let's assume I'm computing the p-value here every time after a sample comes in my trial. So in this case, it's the p-value under the null hypothesis where I have no difference between the two variants that I'm comparing. So in this case, the p-value dropped below the threshold of significance 3 times. It can happen less, it can happen more, but it's pretty likely that in longer trials, it will happen at least once. So if the experimenters follow a strategy in which every time the p-value drops below the significance threshold, they take this as a significant result, then we would really inflate the overall false positive rate much more than the delta that we decided to do in the beginning. So that's not to say that wanting to monitor continuously doesn't make sense. It does, but we just need to do this correctly. So now, with these constraints in mind, or with these desires in mind, that we want to do things adaptively, I would like to reformulate the problem of identifying all the variants, if any, that are better than the control, while being able to stop at the data-dependent moment, we're keeping the probability of making a mistake low, below at most delta, and by optimizing adaptively the allocation of the users to the variants. And when it comes to doing adaptive sampling and adaptive stopping, we typically like to think that the data is IID, but there is a little challenge here that the data in reality in the live streams of global traffic exhibits seasonality patterns, and even within the same day. So here, for example, I'm showing the click-through rate per 6 hours of the day. So you see there is quite a large fluctuation. So if we would be sampling adaptively, it could be that we sample some of the variants at maybe high seasonality and some other variants at a low seasonality, and that could create problems. Or if we want to stop adaptively, again, it could be that we stop before we even get to see all the variants for all the seasons. So we do need to take seasonality somehow into account. And one way to do this is by thinking that each season represents a population, some subpopulations of our customer bases. So that's going to be people that live in different time zones, different countries, interact differently with the website. And now with this, if I have J subpopulations, each of the variants is going to be a mixture of J distribution. So it's not going to be one distribution, but a mixture. And then the value of each variant is going to be the weighted average of the value among each of the seasons. And the weight here is this alpha, which is the frequency or the natural proportion at which that subpopulation appears in my sample, in my data. And something else that is very important when we want to learn adaptively with subpopulations is how we can interact with these subpopulations. Now, if I move from the left side, I can start with a powerful interaction mode in which I'm not only able to pick a variant, but I'm also able to pick a subpopulation at any time. And then I can decide at will to pick these subpopulations that will facilitate my learning, which of course it means that in the end, I might end up with a sample in which the subpopulations are not represented in the same proportions as they would naturally occur. So this is the active mode. The more realistic mode of interaction is what we call proportional here, in which we first observe the subpopulation and then we pick a variant given this subpopulation. And in this case, we are of course restricted to the observed frequencies that each of the seasons appear. A last mode of interaction, which is a bit doomed as well, is the oblivious or the seasonality, the subpopulation unaware version, in which we pick a variant that we never get to see what the subpopulations are. And in this case, the oblivious mode considers that we actually have one distribution instead of a mixture of distributions. It might be intuitive to some of you that as we move from the left to the from the right to the left, we're going towards a more powerful mode of interaction, which, as we'll explain later, has some implications on how much on the sample size that I'm going to need to be able to solve that problem. Yeah, putting it all together now. So the model that we're going to use to describe, to incorporate the subpopulations is a bandit model that has been used a lot in the literature. It helps us do adaptive sampling and stopping, but at this time we need to incorporate the notion of subpopulations. So we do this by having our model consists of a matrix, which is a k+1 matrix of variants, and J subpopulations. This is our reward distributions. You can think of it as Bernoulli right now, because in this talk I'll be talking about Bernoulli. And we also have a vector alpha, which represents the empirical frequencies, the observed frequencies of our subpopulations. The correct answer on this bandit model is going to be the subset of the arms that are different from the control, whose overall value is higher than the value of the control. And as a reminder, we want to do this, we want to get to this answer in a correct way and as efficiently as possible. But how efficiently can we do this? Like if I know the mu, can I know how hard the problem is? And the answer is that I do. So this is something that this is a known result, and we're also extending it in the paper for the case of the subpopulations. So for any sampling strategy for a particular model mu, the expected number of rounds, or the sample complexity, as we call it, this E of mu, gets a lower value. So we can never do better than this lower value of minimum sample complexity. And this value depends, first of all, on the bandit mu, and in particular on this delta between the control and the other variants, right? The smaller that delta, the more samples I will need to distinguish between them. And another factor that plays a role is the proportions with which I'm sampling. It will get minimized when I sample with an optimal way, these optimal proportions that depend again on the model mu and on the interaction with the subpopulations. I'm gonna give you an example now of what this actually means. Let's assume we have this vector, this matrix of rewards, Bernoulli rewards. So I have three arms here, and which is vertically, and two subpopulations that appear in frequency 50-50 as well. So this is the control arm. This is variant 1 and variant 2 in our previous example. So both of the variants are better than the control, consistently actually across all the seasons. But the variant 1 is closer to the control than variant 2. So what we would expect as a good strategy is a strategy that allocates more samples to control and to arm 0 and 1, and fewer samples to arm 2. So what the optimal active allocation would be is indeed it throws more samples to arm 0 and 1, but it also requests more samples in season 1, or in subpopulation 1, I'm using it interchangeably in this talk, which has actually higher variance than the season 2. And as such, because it got more samples actually proportionally for season 1, as you see overall, this vector, these proportions across the seasonality 1 are not going to sum up to 0.5, which is the observed frequency, but because this will facilitate the learning. Now, the proportional case does constrain that the sum of all these weights here per season have to sum up to their observed frequencies. And as a result, again, there is similar pattern that it throws more samples in arm 0 and 1, but it's not able anymore to use as many samples as it would like for the first season. And as you see, actually in the second season, the first arm, it actually gives higher proportion. The last category, the last case would be the oblivious, in which we don't even see the original model. We see this mixture of two Bernoullis, which is another Bernoulli. And there it would simply just allocate samples per action or per arm and ignore completely the whole subpopulation idea. Now, what I'm also showing under each of these proportions is the minimum sample complexity of each of these modes. And what you see is that the active one is lower sample complexity than the proportional and lower than the oblivious. And this is another thing we generalize in the papers. We know that for specific bandit model mu, the more powerful the interaction mode, the lower the sample complexity it will incur. So this whole analysis is done when we actually know the reward distributions mu. So this gives us an idea about how well we can do when we know the mu's, but in reality, we don't really know the mu's. So we need to have an algorithm that over time is gonna get us there, is gonna get us to the correct answer, but without wasting, trying to reach this minimum sample complexity. So there is a standard algorithm in literature, the track and stop, that does this, and we extend it again in the paper for the case of subpopulation, which in a nutshell, for every time point t, it computes the current estimates mu hat. It estimates the target weights based on this estimate. And he picks an arm such as that the empirical proportions, the empirical draws, the draws of these arms will eventually reach these target proportions. And then in the end, for recommendation, we can do two things. We can either stop when there is enough statistical evidence above a certain threshold, or we can do what we're actually doing here, which is that for every point in time, we can actually recommend as a correct solution the arms that are currently better than the control. But we can accompany this with a risk assessment. So what's the probability that I'm probably going to make a mistake with this solution? And to find this risk assessment, what I need to do is to think like, what is the value of delta of the confidence that I would need to have so that my statistical evidence is higher than the threshold. So I would need to solve for delta. That's exactly how we validated our approach on a real ABN experiment that we did in booking a couple of years ago. This experiment was one control against two variants. We were trying to declutter the text when describing some policies to help our customers understand better what these policies actually meant. Both variants were better than the control. So the correct answer here would be 1 and 2. And what I'm plotting here is for each of these sampling policies and modes of interaction, how the risk assessment of the methods changes as the sample size increases, as the samples increase. So the lower the risk assessment, the more confident the sampling policy would be in its recommendations. So all of the policies recommend the correct answer, but of course you see that this happens with a different a risk assessment. So the active policy would start being more confident sooner than the other methods. In this particular case, proportional and oblivious, in this instance that we ran, they didn't show any big differences. And we also tried a uniform case where we allocated uniformly the samples, in which case with that particular sample size we had at hand, it never managed to drop its risk assessment below the 68% approximately. With more samples, it would have dropped, of course, but it just needed more samples to be more certain. So as a conclusion, this was, for us, it looked like a successful experiment. And further on, we went ahead and we implemented actually this platform in booking. The reason why we did is because we know that it's more efficient than using a non-adaptive setup. We're more efficient with our samples. Also being subpopulation or seasonality aware makes it is better than not being more, makes it correct, but also more efficient than if we're not aware of seasonality. And the other advantage is that the experimenter can now monitor their experiments continuously, knowing a risk assessment without actually increasing the probability of making a mistake. We have a long way to go. We have run a couple of experiments right now that we validated also in the non-adaptive platform, and the results agreed. So that's very promising. But there's just a long way to go. We have a lot of problems here. I'm just naming a few, but there would be many, many more. And if you're interested in this, please come and talk to me later. For the time, thank you. I have links to the paper and to the booking blog if you want to see also more of this type of work that we're doing there. And I'm happy to take questions.
Yes, thank you, Christina. Fascinating. Subpopulations. I'm very much wondering what subpopulations are, to be honest. But let me first see if there's questions in the room. Peter.
That was very nice. Thank you. So I was a bit puzzled by the graph you showed. Why are the lines straight for such a long time? What happens there? Or is this related to that you need to have certain threshold before you even start?
I was hoping this question will come, actually. Yeah. The reason why they are straight is because we are actually a property we want these risk assessment curves to have is that they are monotonically decreasing. So we have to cap them, and we can't allow them to increase over time. So we always take the minimum value that once they hit a minimum value, they can never go higher. So it means that while they are flat, we haven't received any more evidence to drop that risk assessment even more.
So that means that you have here, like, you started, I guess, 800,000 or something, or 80,000.
Yeah, here I'm starting, yeah, later, yeah.
And that means that between 80,000 and 100,000, you never get better than the best you had been in the past.
Yes,
Okay, then it makes sense.
exactly.
Okay, thank you.
Yes. More questions? Alexander?
I've got a question regarding the graph as well. So if you can go back. So
This graph, right?
Yeah.
Let me stay here.
I just wonder, so the oblivious one and the proportional one, they look quite close to each other. So do you have is there any reason why? I would think that the
Yeah.
proportional one would do much better.
No, indeed. So we do expect that the oblivious is going to have, in expectation, higher sample complexity. It would require more sample than the proportional mode. But here, the caveat is that we run this just once. It's just one run. So it could, of course, happen even that sometimes the oblivious might actually terminate faster than the proportional, or it could even happen that it terminates faster than the active. But this is one particular instance. Like if I would repeat this run multiple times, we would actually see. And as we actually look at it in the paper with simulations, we do see a difference there in expectation.
Okay, thanks.
But yeah, it's we were also puzzled when we were looking at this last year.
Any other questions in the room? Anyone? Wouter?
Hi, Christina. So I'm curious, what do you imagine that users would do with this risk assessment? They see these numbers coming in and sometimes they drop. So the traditional thing would be to pick a threshold in advance and to wait until they drop below. But what extra uses can you imagine when you have this full curve sort of appearing before you?
First of all, it could be both. Like I can imagine both uses. Like either people who stick to a 0.1, let's say 10% delta risk or a 5% risk, and then just wait patiently until the experiment stops. But then they know that while they're viewing the experiment, they're not really making any dangerous conclusion. But on the other hand, with the risk, I think what happens with the risk assessment is that it just gives them the chance to adjust a little bit their, not just their expectation, but the risk, well, the advantage of risk assessment is that different teams have different appetite for discovery in a way. So some teams are have more sample size, so they are patient enough to wait, and the more mature product, so they could wait for a low until a low risk assessment is reached. But some other teams, they might value velocity as more important than risk assessment, so they might be willing to take more risks for that. So for these teams, maybe a 30% risk is fine, and maybe that's also fine for the rest of the company as long as we are aware that this was a risky decision. And at least this is how I see right now this being used. And in my opinion, this is much better than just assuming that an experiment is significantly positive when it's not. So at least we know that, if this makes sense.
Thanks. I'm wondering, once this experiment has finished, I'm wondering how you summarize the inferences for the data scientist who's going to be making a decision about this experiment. Do you still provide point estimates and confidence intervals? And if so, do you have to adjust them for the adaptive design?
Yeah, so we've also thought a lot about this actually, because in the end, the A/B experimentation is not purely for decision making, right? It's also to learn effect sizes. So, but the way that we decided to at least start using this is to use it as the decision making step, because actually, after all, that's what we are trying to optimize, right? This is our problem is, give me the subset of arms that are better. It doesn't tell me, give me the true values of these arms. So we decided to go with like this adaptive experiment as a first step to maybe even pre-select the subset of options that are useful for us. And then if the teams are interested in knowing effect size, then they would have to go into the standard traditional A/B platform where they would run the control against the winning variant to estimate these types of, to have these inferences. But yeah,
Great,
it's,
thank you.
Yeah, so thanks. So my concern is with choosing what subpopulations to include, because I can quickly imagine, okay, let's add gender, geographic location, customer segments, if you keep going. Like at what point does it break down? At some point, I guess there's too many categories. Have you looked at that?
we have considered this, of course. So, well, I don't have a good answer for you right now. Just as I'll try to say that we consider first the subpopulations that we believe that they are important for this particular for this interaction with the variant. On the other hand, there are also certain types of subpopulations we don't have access to, or we would not be allowed to even use. So that also makes things a bit easier on the other hand. But in general, the correct strategy would be to use everything that would explain the heterogeneity in your data. But we can't know that. Yes. Very good. Very good question.
Thanks.
Okay.
Thank you.
With that, I would like to thank Christina again for answering all your questions as far as time was allowed, and
Thank
for a
you.
very nice presentation. So thank you.